What's going on, guys? Let's look at this problem right here. Here this question is asking, calculate the position of Fermi energy level in n-type silicon at T is equal to 300 degree Kelvin with respect to the intrinsic Fermi energy level. Okay, here they are saying we are trying to find the position of Fermi energy level, that is EF, and also with respect to intrinsic Fermi energy level, so this is EI. So we have to find an equation that is related to EF and EI, and also we have to find an equation that is related to intrinsic concentration. And there are some equations related to this Fermi energy level questions, but the one that is very suitable for this one is this one: EF minus EI is equal to KT ln of NO divided by NI. Okay, here we have intrinsic concentration, and also we have intrinsic energy level, Fermi energy level, and also we have Fermi energy level. So we can, from this one, we can find the location of this Fermi energy level with respect to intrinsic Fermi energy level. Okay, now K is nothing but this Boltzmann constant, and T is temperature, NO is number of electron. Here we have donor, number of donors given, donors added, so that we can approximate this one, like NO is approximately equal to 2 times 10 to the power of 17 per centimeter cube. So this is going to be the NO value. And intrinsic concentration, so this is a predetermined value, like for silicon at room temperature 300 degree Kelvin, this value goes, Ni value is going to be this one. This is 1.5 times 10 to the power of 10 per centimeter cube at T is equal to 300 degree Kelvin. Okay, so we have these two values, and also we have the Boltzmann constant, that's we know that constant, and also we know the temperature, that is 300 Kelvin, so we can find out the location. Okay, now let's go ahead and plug the values. This is going to be Boltzmann constant is 8.62 times 10 to the power of minus 5, and the temperature is 300, and ln of NO, that is this one, NO is equal to ND is equal to NO, right? So that's equal to 2 times 10 to the power of 17, 2 times 10 to the power of 17 divided by Ni, that is 1.5 times 10 to the power of 10, and when we simplify this one, we are going to get 0.424 electron volts. So this is EF minus EI. Now let's look at the diagram. So here we have a conduction band and valence band. Okay, the top part is conduction band and this is valence band, and intrinsic energy level always in the middle of this one, right? Intrinsic energy level is always in the middle, and then we are going to have this Fermi energy level like little bit above Fermi energy level, like this intrinsic Fermi energy level, so we somewhere right here, and the distance we found out, that is equal to 0.424 electron volts, right? So this is the one we are interested, this is the location we are interested in. So with respect to this one, if we rearrange this equation, we are going to have EF is we are interested in it, that is Fermi energy level. That's going to be equal to what? If I move this negative EI to this side, that's going to be 0.424 electron volts plus EI. You can see this is EI plus this one, that is the EF location. This is the EF. Okay, and that's how we do this kind of problems. I hope this helps. Thanks for watching.